Good morning, everybody. Thanks for joining us today for our NUIT Tech Talk on Trends in Research Data Mobility. I'm Christina Bello with the NUIT Communications team and have with me today's presenters, Pascal and Matt. Before we begin the presentation today, if you're having any trouble hearing me or our presenters, please make sure your volume is adjusted accordingly. Either it's up all the way, or if you're using headphones or speakers, those are disconnected. Also, make sure you're using a wired internet connection if that's available. Just will give you the best connection during the presentation today. And also, if you have any applications connected to the internet, email, any other web browsers, we suggest closing those as well. Again, just for the best connection. If you have a question at any time during the presentation, you can type them into the Q&A box here, and we'll answer those throughout the presentation today. After the presentation, we'll also give you an opportunity to download the PowerPoint that we're going to go through. There's a lot of great information and some good graphics in there that we want to make sure you have access to after the presentation. We're also recording the event, so we'll have that available later today or tomorrow that you can watch or share or go back to as you like. But before we get started, we have 3 quick poll questions that we want to get your input on before we start the presentation. So our first question is, what is your role at the university? You can actually select as many of these as apply: faculty, researchers, staff, student, other. Great, looks like a good mix of people. And you do select other, if you want to type it into the Q&A box what your role is, just so we know kind of who our audience is during the presentation today. That will just help us make sure we address all our different audiences. Great. Looks like a lot of staff members, some faculty, some research, a couple students. Great. All right, and I'll move on to the next question here. So for those of you who do research, faculty members, possibly some staff members as well, we want to know, do you collaborate with research partners outside of the university? So I'll give you all a moment to answer that question. It's pretty likely, I would assume, that for most researchers this is somewhat common, but we just want to get a sense of kind of how popular this is as a mode in your research. Okay. So one more moment to answer that question. Great. All right, and our last question for today, our last poll question, I should say, is, do you, and this might be very specific to some of you, do you expect to use data network services on campus as part of the science workflow in your research? And if the question, if you understand the question, great, and you can answer that clearly. If you're unsure, you can check that as well, and we'll address this a little bit during the presentation today to make that clear if that's something you may or may something that you may be interested in using for your research. Okay, great. Looks like we definitely do have some people that do use the data network services, which is fantastic. All right, great. Well, with that, I will hand it over to Pascal.
All right. I would like to welcome people on this installment of Tech Talk. My name is Pascal Pascus. I'm a senior high-performance computing specialist here at Northwestern University. With me today is Matt Wilson, who is the senior engineer, network engineer in telecommunications and networking services. Good morning, everyone. All right, the topic before us today, it's titled Trends in Research Data Mobility. And I'm sure by now all of you realize that the title that is in front of you today is different than the one posted online. The reason for that is because we felt the original title was a little bit too restrictive on the type of things that we would like to share with you today. Here's a brief overview of what we're going to be discussing today. 3 major topics. The first one is basically we're going to be discussing big data flows and how dedicated research networks empower them. The second part of the discussion will focus on the Chicago region as a research network hub and how important this is for Northwestern University researchers. And Matt is going to give us a preview of Northwestern Pilot Campus Research Network that is currently on deployment. Now, let's narrow the focus a little bit on our talk. We're going to be focusing on what we call data-driven scientific research. And the reason for that is because data-driven scientific research accounts for a large fraction of the utilization and generation of big data nowadays. That is not to say that the data-driven scientific research is not just as important. It's just that the focus of the day is to talk about networks and infrastructure that will facilitate big data mobility. Now, my next slide is the most involved slide, and I'll probably take a few more minutes above average to discuss this because it's a very dense slide, and my hopes is by the end of my segment, this slide will be unpacked into the information that it contains. What you see here is a graph, a kind of like general abstract graph. On the y-axis, we plot the scale of science versus demand on CI. Now, CI stands for cyber infrastructure and generally references the number of compute nodes, racks, disk cooling, etc. The scale of science is again a generic term that refers to the degree of the problem complexity or problem solution complexity. Problem size, problem detail, inclusion of more physical processes that you would like to model or analyze. And typically, these kind of problems lead to a much bigger impact on scientific discovery. And what this graph shows you is that to accommodate large scales of science, one needs to scale up to larger and larger computing capacity, which on its own increases the strain on the cyber infrastructure. Now, the bubble size differentiates in the diversity across disciplines and within a discipline of a problem type. So diversity will drop because only as you go to higher scales of science, because only a small fraction of problems require the kind of extended cyber infrastructure to discover a path to solution. So along this backbone of computing capacity, data are generated, collected, and analyzed, and data mined. And data flows from across all different scales of computing capacity. The reasons why the data flows are a lot, and we're going to try to cover them as much as possible. But in general, data will migrate upwards towards larger scales as researchers try to extend the problem size, speed up the path to solution. And reasons why data cascade down is when we try to aggregate data, distribute data with other collaborative partners, realize that we need to cater to a long-term storage of our data. And not only that, in addition to that, cyber infrastructure is not a static entity. Hardware gets recycled, gets replaced. A supercomputer that is here today will be out of decommissioning like 5 years from now. And so the data cannot stay on those high-end computing facilities forever. And if data needs to be preserved, they need to migrate downwards towards local storage or cloud storage solutions. In this equation, big data enters into the picture because typically large scales of science will generate more data, or large scales of science will use big data for their investigations. On the next graph, we come to the part where we're discussing trends. As you can see from the graph on the right, the trend is that big data flows or big flows are projected to increase in order of magnitude every 4 years. And therefore, cyber infrastructure has to meet the demand on local, regional, national, or even international level to accommodate to that. Now, if you look at the vertical scale, we're talking about petabytes of information, petabytes of data. Now, most people nowadays, the normative size of files is probably a gigabyte. So a petabyte is about 1 million gigabytes that we can think about. Now, as these data flows flow through our existing networks, it puts strains on them. And the networks have to adapt, have to be extended to accommodate that. Now, why big data mobility is critical? Well, it's critical Where is it critical? It's critical in academic research. I have just given briefly 4 examples. LHSC, which stands for Large Hadron Collider, the up in CERN that does high energy physics. They're responsible for the discovery of the Higgs boson last year. Typically moves about 25 petabytes between the major research sites at the collider to the collaborative locations. The LSST, which stands for the Large Synoptic Skies Survey Telescope, that is currently being built down in Chile, will need to transfer about 20 terabytes of observations from down to the plateaus of the Atacama Desert, all the way up to the University of Illinois in Urbana-Champaign, 20 terabytes nightly. That's a big amount of data to be transferred in a regular amount of intervals. NASA maintains humongous databases of climatological data, either by observations from weather satellites and stations and modeling.
Okay, hopefully you all can hear me now. Sorry about that. Unexpected little mic issue. So again, sorry for the interruption, and Pascal, I will pass it over to you. Hopefully everybody can hear us.
I'm not sure exactly where they connected the.
So let's start back at the beginning of this slide. I think would be good.
On the drivers research level.
Yeah.
All right. Again, we apologizing for the technical problems. I am sure that if we had a large resource network connecting our mic to the computer, we might not have had these issues. But let's continue on with the slide that we think the connection was interrupted, which was called the drivers of research data mobility. Now, research results by the method of being research, and especially scientific research, should be reproducible and designed to be extensible. One other reason why research data have to be mobile is because the local infrastructure that supports the generation, collection, and analyzing of those data have limits. Also, we need to foster collaborations. Collaborations that are typically promoted by federal funding policies. Let me explain that because it can be very important, especially to researchers. Federal funding policies nowadays advocate for researchers to come together to submit grants for funding. They strongly encourage cross-institutional and cross-discipline collaboration. And not to say that, if you don't do that, you're not going to get the money from the federal government. It's just that they look favorably upon these conditions. So the collaborations are basically promoted by federal funding policies. And not only that, the federal policies come into place in one more aspect, which is mandates that says that if you generate data by a federally funded project, you need to be able to preserve that data for a number of years, typically 5. So that means that if you generate those data in some other machine, and that machine is going out of commission or your project is ended, you need to have an ability to move the data to a safer location from where to preserve it for the, the remaining of the time that the NSF, the National Science Foundation, mandates. Another reason why we foster collaboration is the fact that the core competencies and resources are cross-institutional and cross-discipline. And researchers understand this very well, and they try to leverage them at any opportunity possible. Another way, an additional 2 points is that data and applications that advance research benefit from open access, which means the researchers should be able to go and grab a scientific data set from some central repository in order to do something with it. Those data sets typically are the effect of aggregating the data in a community data sets or centralized repositories. Now, all of these things are contingent upon, in order to share, move data, for whatever reason you move the data, you need to actually push this data through a network. So it is important for us to just give you a very broad definition of what a network is. A network is a collection of infrastructure elements that basically takes the data and allows them to be transmitted from one location to another. And what is the main 2 constituents of that? Well, you will have the hardware, which are all the cables, the servers, the routers, switches, bridges, but I wish we had the time to explain what each and every one is doing, but if you guys get the presentation, the answer is a 1 Google question away. All of this hardware has to be arranged in a kind of an optimal physical topology in order for the data to seamlessly go from one location to another. On top of that hardware, we have transport protocols and software that administer the internal functions of how this communication goes. An example is TCP, which is, what is it, TCP, Transmission Control Protocol. Transmission Control Protocol, that's right. And the handle of data stream, let's say Globus Online, which is based on grid FTP technology. Now, how do we qualify a network? Well, there's many qualifiers for a network, but we're just going to use the major 2 of them. It's basically qualified by the bandwidth, or what we call the maximum throughput, and that's basically the rate by which bits of information is transmitted through a communication path. The next part is the latency, which is how much of a round-trip delay in the propagation of a signal those packets will encounter. This would be due to maybe final signal speed. Remember, if you have a fiber optic cable, which is effectively glass and light goes through them, you have the speed of light within that medium. There's also other factors that are the delay, time sitting in the queue for those packets to be put on the network and be transported, time to process the signal by hardware. In fact, in most modern hardware, most of the delay comes from that process, that the signal at the end points have to be reprocessed by intervening hardware. For example, convert light signal to digital signal, write the data to the disk. At this point, we are going to define the dedicated network, and there is a way we're going to approach that definition is to compare to a general purpose or commodity network that we are actually kind of accustomed to when we connect to the internet through our router at home. We are basically accessing the commercial commodity network that allows us to view websites and download files. So compared to a general purpose commodity network, a dedicated research network only transports research data. So it doesn't, it will not allow, and it doesn't want to allow anything like, say, access to a website, or passing email through, or any kind of like copying of files that are not research data related. The dedicated research network are typically non-commercial, so it is basically used only for academic research, and it's optimized for large data flows. Large data flows, so the technical jargon, or I think the network engineers like to use, called an elephant flow versus a mouse flow, which is the smaller data flows that you will encounter typically on general purpose or commodity network. Continuing on with the definition of how the dedicated research network differentiates from the commodity network, typically the research network will use advanced high-performance infrastructure to minimize things that are of extremely important, let's say latency. You want your data, large volumes of data, to go from point A to point B in the shortest amount of time. And other than that, you need to increase the possible size of that data as much as possible so you can do it in a much more efficient way. You want to avoid congestion. You don't want to have too many packets of information, clogging up the communication pipe. And other than that, the most important thing, at least in my opinion, that a DRM has to account for is to prevent packet loss. In fact, you do not want any packet loss when you're doing research data transfer. A single packet may make an entire data set unusable. And the way that they can do this is by continuously monitoring the performance of the network. The DRMs also allows for requirements for interactivity. For example, the research needs to connect to a machine, load up the data, visualize them, and do some work on that data. And that interactivity is greatly facilitated by the greater bandwidth that typically is employed by a dedicated research network. Or research might want to do experiment control. For example, let's say you have a seismologist that wants to access equipment on the field and continuously monitor the data stream that comes out from those sensors. And last but not least, we feel it's important to also tell you that the DRM typically will not employ a firewall for inspection of incoming data, with the understanding that this is research data is concerned, and since the traffic is only restricted to research data themselves, the typical wisdom is that we don't really need to inspect them for any kind of malware or any kind of not allowed traffic. Now, this graph looks similar to the one I presented earlier, which is, again, what kind of a scale of science and the demand of CI could be performed by the typical network capacities that are currently deployed. So for Northwestern's pilot research, campus research network, we're talking about a high-performance dedicated network at the speed of 10 gigabits per second. Now, as you increase if you want to go to larger and larger scales of science, in order to get the same kind of performance for the researchers to move the data, that size increase by orders of magnitude. So basically, high-performance research network at the national and international level are being constructed to allow 10 gigabit per second flows. Now, this next generic graphic just gives you an idea of how research gets partitioned within a particular institution. And this is modeled after Northwestern University. So research, and remember we're talking about data-driven research, will typically be done either on local group clusters, personal desktops, or for a lot of researchers, they will move that data or do some data analysis or generation on the central cyber infrastructure facility. Let's say our HPC cluster Quest resides in that data center. It's in our central high-performance computing resource. But of course, the research, due to collaborative efforts or because you want to scale the problem to a bigger computing capacity, some point the research has to migrate outside that silo of research. So it has to go to the outside world and be piped towards federated resources, let's say Exceed, an academic or industry partner, or if you want to leverage the cloud computing and storage services, you want to do that as well. Here's 3 examples of how research network basically, when you add them into the mix, greatly facilitate research data traffic. If you have, within a particular university, if you have group A that wants to collaborate with group B, and they want to send some data between them, if they don't have a dedicated research network to do that, that data has to share a communication path with other traffic that is not typically relevant to the problem, let's say email or internet. So a campus research network itself allows for this high volume research data flows to flow from within a campus between group A to group B. The same paradigm, of course, applies to inter-campus collaboration between two groups. A campus research network will provide you access to, let's say, a high-speed regional or national network, and the large data flow would flow from that institution to the other institution if there is a, in order to foster a collaborative environment. And a much more, macro scale view of this project, let's say you have a central repository that contains some data, some, let's say, biomedical data. And we have all these research institutions that will need to go and access them, where the optimal solution, the way that you would ideally want to do that, is you want to have these research institutions connected to dedicated research networks onto main super highways of traffic, let's say a national or regional high-speed network, and follow that path to get the data back and forth in the repository. Now, these main superhighways of regional or national networks typically sometimes intersect on hubs, let's say the Chicago region, and that allows you for data to seamlessly pass from one communication path to the other. Now, the last figure kind of like encapsulates pretty much the fact that, yes, I'd like to share my data, I'd like to migrate my data or cascade my data from other facilities. How do I do that? What are my possible options? So academia is down below. We have all these academic institutions generating or analyzing data. Researchers will always share data with each other. Those blue dots in the point in the bottom reflect that practice, which is data will flow from one academic institution to another all the time. There will be times where critical research that had a large scale of science, as we mentioned before, motivated by those red circles, will exceed the local capacity of the research institutions. And what happens then? That data need to be, if we need to do these computations, this analysis, they have to be moved to another facility that is exceeding the general scope of academia. In general, we are talking about three possible options. You can use cloud computing, which is private industry. You can use a federated or academic center or a supercomputer. And these are academically, they're housed typically in academia, but they're directly funded by the federal government. And there is also the option of the national lab, high-performance computing centers or supercomputers. These are typically called federated funded research and development centers. These are the national lab, let's say Los Alamos or Livermore National Lab. And these guys, we have a big sign here, typically they reside behind a wall. So not everybody can gain access to these facilities. Typically, you either need to work for the government or have some government affiliated person within the wall to do the research that you would like to do. The three stars on the side refer to the fact that you can gain access to the federated HPC by the merit of a proposal. That means you submit a proposal that state why would research benefit if you take your code and your data and move it at that particular level. If you get the approval of a selection committee, then you can migrate your data, your codes, generate them here, and then push them back to your academic institution. But if you have money to spend, a cloud computing will allow you to do exactly the same thing without really bothering to see whether your scientific project actually has any merit. You are the one who determines the merit of your own application and your data. So if you have the money to spend, you can take your research and migrate it to cloud computing services and perform the computations and the analysis and everything there. And with that note, I will now pass the word to Matt Wilson, who will segue the conversation into examples of research networks.
Thank you, Pascal. I wanted to spend a very brief amount of time before we move to questions talking a little bit about specifically what we're doing at Northwestern University and how some networks are in place today and available for use for this type of traffic. Briefly, I want to discuss examples of different types of research networks. When we're looking at the national level, in the United States, we have groups like Internet 2 and also the U.S. Department of Energy's Energy Sciences Network, or HPSNet, which essentially span the continental United States and provide a high-performance superhighway backbone for research traffic. But certainly this is not limited to just the United States. Other countries have their own backbone networks. For example, in Canada, that network is called CANARY. That's Canada's wide area network. In most cases, the way that institutions and organizations get access to these high-speed national backbones is through a regional connector network. In Chicago, there are several, and two of the major ones that Northwestern is directly connected to are MREN, the Metropolitan Research and Education Network, and the CIC Omnipop. CIC stands for the Committee on Institutional Cooperation, which is essentially the Big Ten schools plus the University of Chicago. And through these regional networks, Northwestern has connectivity to national backbones like Internet 2, HPSNet, as well as communication with other partners. So, for example, if you want to get to Fermilab in the area, or you want to get to UIUC, Northwestern would be connecting and sending data to and from that institution through one of these regional networks. We're also very fortunate to have international high-speed backbones. Starlight, which I'll talk a little bit more about in a couple of slides, is actually housed at Northwestern on the Chicago campus. But there are other networks such as AmLight, which connects North and South America, and Géant is in Europe. It's essentially an equivalent to Internet 2, but it's multinational as it spans European nations. Just wanted to very quickly throw up a couple of pictures. This is something you could certainly look at afterwards from the slides, or as Pascal said earlier, Google is a good option as well. But Internet 2 as a national network has presence across the continental United States and a number of interconnection points. AmLight is an international research network. You can see the connectivity here between North America and South America. And this might be a path for, say, the LSST data that Pascal was talking about earlier. But certainly, North America is not the only game in town for international networks. There are networks that go across the Pacific and the Atlantic to Europe and Asia and points in between. Gloriad is one of those international networks. Briefly, we're in a unique position because ICARE, the International Center for Advanced Internet Research, is at Northwestern. It allows us to not only have access at Northwestern itself, it helps establish Chicago as a premier hub for international research traffic. As I mentioned before, MREN is a regional network in Chicago, and most major research networks in North America are present at Starlight or in Chicago. So the fact that we have Starlight, the optical star tap, on NU Chicago campus creates a resource that is very easy for us to take advantage of. And it provides a modern, high-speed network dedicated for researchers and research traffic. Specifically at Northwestern, the problem for us is less about trying to build large, long-haul optical networks to get from somewhere in Nebraska to some interconnection point to get on the superhighway. Instead, the problem for us at Northwestern is generally a last-mile problem. We do not have any dedicated bandwidth for research traffic between the Chicago and Evanston campuses. All of the great regional, national, and international network connectivity is down in Chicago. Most of the strong research facilities are on the Evanston campus at Northwestern. So it's important to us to provide dedicated bandwidth between the two campuses, either to allow researchers on the Chicago campus to get up to things like Quest HPC in Evanston, or to allow folks in Evanston to be able to get down to Chicago and then to external networks. Also, in most cases, network service to the end user at your desktop is limited to 1 gigabit per second. Northwestern, in a joint proposal with the National Science Foundation between IT and the Office of Research, which was supported by the endorsement of a number of faculty with letters of support, won us a campus cyber infrastructure program grant from the NSF in 2003. And that has allowed us to begin deployment of building out our campus research network plan. This allows us to build a completely separate physical network infrastructure, a separate intercampus backbone, 10 gigabit per second connections to the desktop or cluster on campus. Of course, it lets us leverage the connectivity to external research networks that we enjoy in Chicago. And this network is being designed to support data transfer nodes in the Evanston Data Center.
So we actually just had a great question. Someone asked, is the traffic on MREN, for instance, handled differently than Internet 2, or is it seamless for the researchers? Does it look different depending on which network they're on?
Yeah, I would consider MREN to be sort of an on-ramp to Internet 2, if that's where you need to get. So, for example, if you have a collaborator in Florida, you might go from Northwestern through MREN to the Internet 2 backbone, then drop off maybe at a Florida regional network like Florida Lambda Rail, and then maybe end up at FIU or wherever your collaborator is.
Got it.
But as far as the user is concerned, he doesn't see any of these changes, right?
Yeah, the end users don't necessarily even see where their traffic is traversing. Like, depending on the way that networks attempt to find the best path. So a telephone system generally stands up a circuit. You want to call somebody, it creates a dedicated path. You talk to that person, anything you say into your handset automatically comes out on the other handset. You hang up, the call is done. In a packet switch data network, the data network's allowed to try to use whatever path it can to get data from point A to point B. You're never necessarily building a dedicated circuit for that traffic, and if a node in between the two fails, the data network automatically tries to route around that issue. So you might be sending traffic via MREN today, and tomorrow it might be via the CIC Omnipop.
Got it.
So I'll try to say a couple of brief words about the campus research network model. Again, it's about providing dedicated high-speed connectivity. It's about providing friction-free network paths. You want to avoid contention and packet loss. And the fact that you do not have a firewall is mainly to avoid the firewall as a performance bottleneck. It does not mean that you throw security out the window. You need to design security that is appropriate to the science workflow while still maintaining the performance requirements. Dedicated data transfer nodes are systems with very high performance disk arrays so that they can take advantage of the high-speed network. Generally speaking, if you just plug your laptop in, you're not going to be able to send larger data sets at greater than a gigabit per second. So you need to be investing in the hardware to take advantage of the data network service. And finally, the model includes active performance measurement. So the research community in general has adopted the Perf Sonar software package to leverage this. So if you have a collaborator in another institution, it should be very easy for us to set up scheduled tests between our Perf Sonar server and theirs to verify and confirm that we can get the kind of throughput that we expect from the network.
And we actually had another question, somewhat relating to the last one, about Starlight. And so comparing Starlight to MREN, for instance, is Starlight a dedicated network so you can kind of choose to take that direct path, or is it similar to the MREN one where it chooses the best path?
Yeah, so this is a good question. So it's also possible to create virtual circuits to provide dedicated bandwidth over a specific path. Internet 2, for example, has an advanced layer 2 service which allows you to dynamically schedule virtual circuits. Say I need to send data at 3 gigabits per second between Houston and Chicago. You would log into Internet 2's website and create a virtual circuit. You would say, I need it from Friday night at midnight until next Sunday. The circuit would be created, and any traffic you dropped into one end of the circuit would be sent over that specific path and let out at the other side.
So similar to the telephone example you gave earlier.
Absolutely. A point-to-point link. It's virtualized. You're not getting dedicated access to a physical circuit. It's a virtual slice of the infrastructure that Internet 2 is providing on its high-speed backbone. Those are sort of two approaches to how people want to transfer data, and certainly for long-standing projects or very well-defined data flows, virtual circuits are an excellent solution. This HPSNet overview slide is just trying to give an example of the high-performance science network that we're building on campus today. The maybe important elements to point out here are that the high-performance science network traffic can still get on the NU campus commodity backbone, so your desktop. In most cases, maybe you've moved a research cluster onto a high-performance science network. You may still need to be able to manage that device or get low bandwidth reports out of it. So that connectivity is still available. And the other thing I would point out is that this is a pilot project, and so there are several single points of failure within it today. The NSF grant was generous, but it's not so generous that we're able to provide the same redundancy and reliability guarantees that we have on the production commodity network today. So the future of the campus research network for us is the challenge to expand it beyond the pilot. Today, any additional funding to extend it would have to come from campus researchers, and costs are highly location dependent in that if you're in a location where we already have switch and router gear and fiber optic cabling, we're talking a few $1,000s. If you're in a building where we don't have any service today, the cost increases dramatically. But certainly we want to talk to people about what your needs are, and that really is what's going to win funding for us. The more we can identify and articulate use cases and requirements and needs, the more that I think we can make a good case to budget or grants to get that funding and secure the network services people need to get their science done. And with that, I hope we have left some time for questions.
Yeah, definitely. So I'll open it up for any additional questions. We had some great ones that came in, so thank you for those of you who have those questions. So let's see. So I'll leave this open for just a moment to see if anybody has any questions specific to their area or their research. And I'll actually switch us over to, we have just a couple quick feedback questions, but we can answer any presentation questions while we're doing that as well. So again, putting your questions in if you have those, and we'll just kind of move forward, wrapping things up for the presentation here. So our first feedback question is, did you learn something new during today's event? And I know in the course of working with Matt and Pascal on this presentation, I learned a lot, and this is a huge topic in academia and research and data right now. So we know there's a lot of new information for some of you, but it's getting talked about more and more. So we hope you learned something new. And if there's anything else we can address on this topic, let us know. We're always happy to cover topics like this in more detail. But great, it looks like most of you learned something new, which is always good to see. Okay, and I'll give you one more moment to answer that question, and we'll move on to the second. Okay, and so moving on to the second question here, which is, do you plan to apply any of the information you learned at today's event? And particularly, depending on what your role is at the university, some of this may be applicable to your work, some may not. I'm always happy to talk with you in person or one-on-one to help you understand how this information can be used. If you work with researchers, happy to share information on how this can be applied to different areas of the university. Again, I know this is very research specific, but a lot of it is relevant to a lot of what we do at the university. So we're always happy to talk with you individually about that. But great, it does look like several of you do plan to use some of what we talked about today, which is also good to see as well. All right, and our last question today is, on a scale of 1 to 5, 5 being very satisfied, how would you rate the overall quality of today's event? Ignoring the little audio snafu we had earlier. But again, just let us know if you're happy with this event, if there's anything we can do to improve, let us know. We always take your feedback and use it for future events, topics, anything we could add to these this type of presentation, let us know, and we're always happy to make those changes. We want to make sure you're getting the most relevant and useful information for you out of these. We know it's we want to make it a good use of your time. Great, looks like everybody was pretty happy today. All right, and with that, I'll show you where you can download the PowerPoint, and we'll wrap things up. So if you want to download the presentation, you can click on this file here and click Download Files. It'll open up in a new browser window, and you can open that and download it there. Again, we'll also have the recording of this event available, along with the PowerPoint on the NUIT website later today or tomorrow. So you can access it there, share it as you like. If you have any questions after this event that we didn't cover or that you think of later, if you've watched the recording and look at the presentation, you can email IT-communications. You can contact the support center, and they'll help direct your question to the right person to help answer that for you. And with that, I will say thank you all for attending. Thank you, Matt and Pascal, for a great presentation. And have a wonderful afternoon.
Thank you very much. Pleasure to be with you today.